Hey guys, my name is IBM and today I'm taking you to I think this is going to be lesson 5 of waves and superposition, and I think in lesson 5 we shall concentrate mostly on Doppler effect, the concepts of Doppler effect, the general Doppler effect formula, and things in that line. Do not forget the course outline for AS Physics. For those of you who are doing AS Physics, you should study all these topics to prepare for your AS Physics exams. And currently we are dealing with waves and superposition. All the topics in red have been covered, and only the topics in yellow are the ones which are not yet covered fully. For those of you who are always asking for the tutorials in soft copy, I'm sorry to let you know that it's only my students who access these tutorials in soft copy. However, the tutorials in soft copy are, if you want them, they come at a cost, so they are not really free. So in case you're willing to obtain them, I can give you a link to the website or to the site where you can purchase them from. Okay, so remember we are dealing with waves, and I say this is going to be unit 7. It is unit 7 and this is going to be lesson 5. Remember I said I called the topic waves and superposition. So unit 7 is waves in your syllabus, and unit 8 is superposition. So I'm going to just cover it as waves and superposition. So in lesson 5, like I said, we are going to be looking at Doppler effect. Doppler effect. The concept of Doppler effect is very common to us, and we might also have talked about it briefly in IGCSE, although it may not have been mentioned in much details. However, when you look at the night sky, for example, you observe as if the color of a moving star keeps changing. You might have observed this in everyday life. On a very clear night sky, you would observe that the color of a moving star appears as if it is changing. Of course, you may think it is changing, but actually it is not really. It's not really the color which is changing, but because of there could be relative motion between the star and the observer. Such relative motion gives an impression as if the star is as if the color of the star is actually changing. And also, there are other factors such as refraction between the star and the Earth's surface within the atmosphere that could be considered to explain why it appears as if the color of a moving star is changing. In everyday life, you must have noticed, or you must also have observed, that a siren of an ambulance, a police car, and that of a jet plane appears to increase in pitch as they approach you, whereas it appears to become lower as they go away from you. You might also have observed this in everyday life. As an ambulance approaches you, you notice that the pitch goes extremely high, and as it moves past you, you notice that the pitch extremely goes low. So this phenomenon here are what we call Doppler effect. So this phenomenon is called Doppler effect. So what do we mean by Doppler effect? As the police car approaches you, we are saying that the pitch increases. You hear a very high pitch. And as it moves away from you, there is a lower pitch. So what is happening is motion. There is motion. Therefore, there is relative motion between one object in comparison to the other. Maybe you are standing at a point and the source of sound is moving towards you and moving away from you. That relative motion causes a change, or an apparent or an impression that there is a change in frequency or a change in pitch as the source approaches you and as the source moves away from you. So what we mean by Doppler effect is simply the apparent change. Apparent meaning it may not exactly be true. The apparent change in the frequency of sound when there is relative motion between the source and the observer. So as long as there is relative motion between the source and observer, then uh, we expect or we observe an apparent change in frequency, or the apparent change in the pitch of sound waves as the source and observer are either moving relative to each other. That is what we are going to call Doppler effect. It occurs with sound waves and all electromagnetic waves. So all waves show Doppler effect. Although it is more pronounced with Doppler effect, all waves show Doppler effect. And later on for electromagnetic waves, we may not call it Doppler effect, but we may call it Doppler redshift. That will be a topic called astrophysics and cosmology. So instead of calling it Doppler redshift in waves, we shall call it instead of calling it Doppler effect, which applies to sound waves, we shall call it a Doppler redshift when we talk about electromagnetic waves. Because for electromagnetic waves, the wavelength is going to be more pronounced, or the wavelength is going to be more important than the frequency. However, in both cases, remember that from V equals lambda times F, if V is constant, lambda is inversely proportional to frequency. So frequency and lambda, the frequency determines the wavelength. Therefore, if there's an apparent change in frequency, there is most likely going to be an apparent change in wavelength. So for electromagnetic waves, we shall simply talk about wavelength. Now this animation here is actually showing what happened during a Doppler effect. Let us assume there is an observer standing somewhere here. I'm going to call this observer A, and there's another observer standing somewhere here. I'm going to call this observer B. For observer A, we notice that the waves come closer as the source moves towards the observer. And for observer B, it's like the waves spread further apart as the source moves away from the observer B. So it's like we are going to see that observer B may detect a lower frequency as the source moves away from him, and observer A will detect a high frequency as the source moves towards him. So that's what we mean by a Doppler effect. Let's give a simple analogy of Doppler effect. So let us imagine, we are going to imagine that you are in a boat that is lying at an anchor on a gentle sea where the waves have a period of 2 seconds. What does this mean? If the waves have a period of 2 seconds, it means it takes 2 seconds, or after every 2 seconds, a crest or a trough is going to hit the boat after every 2 seconds. If the waves are moving towards the boat, which is the boat is stationary at an anchor, and the waves are just moving normally towards the boat, and they're hitting the boat after every 2 seconds. This means that every 2 seconds a crest hits your boat, with the water waves moving say towards the boat. So let's say I'm having here the waves coming from the waves on the sea moving towards a stationary boat. I don't remember how to sketch a boat. So the waves are moving, the boat is stationary, so the boat is at rest. The waves are moving towards the boat, and a crest, these lines are showing crests. And after every 2 seconds, a crest is hitting the boat. So if you set the stopwatch at t equals to 0, just as the first crest hits, let's say at t equals 0, the first crest hits the boat. The watch is going to read 2 seconds when the next crest, which is the second one here, hits the boat. The watch will be reading 4 seconds when the third crest hits the boat, and it will read 6 seconds when the fourth crest hits the boat, and so on and so forth. So in that case, we say the frequency is going to be equal to 0.5 hertz. That means half a cycle reaches the boat, the boat in every, remember frequency is the number of cycles per unit time. So it means half a cycle would reach the boat in every second. So it means in 2 seconds, now we can have a full cycle. In 1 second, we can have just half a cycle reaching the boat. Now we are going to assume that you start heading directed into the incoming or into the oncoming waves. The waves are coming towards you and you are now also moving towards them, or you are moving the boat towards them. So you start heading directly into the incoming waves. Number one, you reduce the distance which the crests are going to move to hit the boat. That means if the frequency has not changed, or the number of waves produced by the source has not changed, it means now the waves will hit the boat in a very short period of time. So suppose you start heading directly into the oncoming waves. Again, you set the stopwatch t equals to 0 as the first crest hits the front of your boat. So you are moving towards the waves, and then you set t equals to 0 when the first crest hits the boat. The next crest is going to hit the boat in a shorter time than before. It will now hit the boat in a time less than 2 seconds, as we have seen before, simply because now you are moving towards the waves. You are moving towards the direction from which the waves are coming. So because you are moving towards the next wave crest, as it moves towards you, it hits you less than 2 seconds after the first hit. Imagine you are moving towards a person who is also moving towards you. It means you are going to meet at a certain point in the shortest time possible. So it means the next crest will hit the boat in a time which is less than 2 seconds. So now the time at which the crests are hitting the boat has reduced. So in other words, we say that the period you observe is going to be shorter than 2 seconds, which you had observed when you were stationary. So it's like the period has now reduced. And then remember, from f equals to 1 over t, since you now observe a smaller value of t, then it means there will be a higher wave frequency than when it is at rest. Now, this frequency we are seeing here is not the frequency of the waves produced. It is instead the observed frequency by the observer. Because the observer is the one determining the time or the period, he will record a smaller time. Therefore, he will observe a higher frequency for that matter. On the other hand, let us assume you now move away from the boat. So, like I say, the waves are moving towards the boat. The waves were moving towards the boat, and this time the boat which was here is also moving away from the boat. If the observer starts the stopwatch at t equals to 0 when the first crest hits the boat, since the boat is now moving away, it means the next crest would have to take more time to hit the boat. So if you turn around and move in the same direction as the waves, you observe the opposite effect. So if you set the stopwatch, or if you set your watch at t equals to 0 as the first crest hits the back of the boat, because you are now moving away from the next crest, more than 2 seconds will have elapsed on your watch by the time that that crest catches you. So if t equals to 0 when the first one hits, it is going to take a time which is more than 2 seconds for the second one to hit the boat, because you are moving away from the waves. Imagine if you are moving towards someone, or imagine if you are running away someone who is chasing you. It means that person will have to take more time to reach you, even if he's moving faster. So it means the time t has now become bigger. In that case, from f equals to 1 over t, where f is going to be the frequency detected by the observer who is on the boat, because he's determining or is obtaining a large value of t, then the observer will observe a lower frequency, because frequency is inversely proportional to the time. So these above effects, which I have just described in this analogy, the above effects occur because there is a relative speed. The relative speed between your boat and the waves depend on the direction of travel and on the speed of your boat. So there are two factors here. One is direction and two is the speed. The relative speed between your boat and the waves depend on the direction and the speed of the boat. So relative speed, of course, it means this must be involving a motion. And therefore, when the observer and the source of the sound are both stationary, the number of waves per second reaching the observer will be the same frequency as the source. That is, the frequency of the waves depend on the frequency of the source. That's why we said this was apparent frequency. It is not the actual frequency. So if there is no Doppler effect, if there is no relative motion, the frequency of the waves is the same as the frequency of the source. I have tried to illustrate this here. So when the observer and the source of sound are both stationary, the number of waves per second reaching the observer will be the same frequency as the source. So the number of waves reaching the observer will be the same as the frequency of the source. Remember, frequency is the number of waves per second, or the number of complete oscillations per second. So because the observer in this case is stationary, the distance between the crests is remaining the same, and the number of crests reaching the observer in a given time is going to be the same. This means the frequency is going to be the same as that of the source. So the source, let's assume the source emits waves of wavelength lambda. So whenever you see lambda, it is the wavelength of the source. Then the observer in this case is going to receive or is going to observe waves which have the same wavelength lambda, because the observer is stationary and the source is also stationary. Then in that case, the frequency observed by the observer, which I'll always call f naught, is going to be the same throughout. So we are saying let v be the speed of the sound wave in air, and vs be the speed of the source of the sound wave, and fs to be the frequency of the source. So if the observer is stationary and the source is stationary, we have said that the observed frequency, which is f naught, is going to be the same as the frequency of the source. I'll always use f naught for the frequency which is observed by the observer, and fs to be the frequency of the source. Remember, the frequency of the source would be equal to the speed of the waves from the source divided by the wavelength of the source. But remember, the speed of the source is going to be the same as v, since the observer and the source are stationary, and the wavelength of the waves is simply going to be lambda. Let me just leave it as lambda. Remember, the stationary observer receives waves with the same wavelength lambda if the observer is stationary. So when I make lambda the subject, then the wavelength of the stationary observer in this case is going to be lambda equals to v over fs, making lambda the subject. Now let's try to modify this situation and think of a situation where the source decides, or the source is now moving towards the observer. Let's think of a situation where the source is moving towards an observer. Remember, when the source was stationary and the observer was stationary, the observed wavelength lambda was equal to v over fs, where v is the speed of the waves in air and fs is the frequency of the source. So when the source moves towards the observer, the effect is to shorten the wavelength of the waves reaching the observer. In other words, since they travel a shorter distance before reaching the observer, it's like the wavelength has shortened. So this is what I therefore mean. If the observer was stationary, but the source is moving towards the observer, so for the observer, the distance between the crests is therefore going to be shortened. So the wavelength is going to be shortened. So this shortened wavelength is going to be considered as the observed wavelength. The observer will detect as if the length of a cycle, or the distance traveled by a wavefront in one cycle is very short. And remember, wavelength is the distance traveled by a wavefront in one complete cycle. So when the source moves towards the observer, the effect is to shorten the wavelength. The wavelength is the distance traveled by a wavefront in a one cycle. So because a shorter distance will be now traveled by the wavefronts when the source moves towards the observer, so the observed wavelength is going to be smaller by a certain value. So let us assume that the source was moving towards the observer by speed vs. Then the distance moved by the wave, which I'm going to call delta lambda, is going to be vs divided by vs divided by fs, just using lambda equals to v over s over frequency, where vs is the speed of the source and fs is the frequency of the source. That is going to be the distance moved by the wave, because remember, distance moved by a wavefront is equal to the distance moved by a wavefront is the wavelength, which is equal to v over f. So this is going to be the speed of the source and the frequency of the source. But do not forget, when we had a stationary source and a stationary observer, the wavelength was v over fs, where v was the speed in air, not the speed of the source. So what is therefore the observed wavelength, or what is the relationship between the observed wavelength and then the speeds? So in this case, therefore, the observed wavelength lambda naught, we shall get the wavelength that we observed before when the source was stationary and the observer was stationary. We subtract the change, or the distance which the source has moved by the time the observer receives the waves, which I'm going to call delta lambda. Or in other words, the distance delta lambda is supposed to be equal to the wavelength minus the observed frequency lambda naught. That is the distance moved by the waves, or by the wavefronts, by the time the observer detects them. It's the difference between the actual wavelength minus the observed wavelength if the source is moving towards the observer. So making lambda the subject, it means the observed wavelength is equal to lambda minus the distance moved by a wave, or by the wavefront. So when I substitute for lambda, which is Vs over Fs, and I also substitute for for lambda, for changing lambda, so I'm having something like this: lambda naught equals to, where there is lambda, I'm putting there V over Fs minus the distance moved by the wavefront when the source moves towards the observer, which is Vs minus Fs. So when I make lambda the subject, when I simplify this, considering the square root, this becomes V minus Vs over Fs, because Fs will be the square root. So that's how I come up with this as the observed wavelength, which is going to be considered as the apparent wavelength. So the apparent wavelength is equal to the difference between the speed in air over the speed of the waves in air minus the speed of the source divided by the frequency of the source. So if we want to find therefore apparent frequency, the apparent frequency will now be the relative speed, or the relative velocity, the velocity of the wave relative to the observer, divided by the apparent wavelength of the wave reaching the observer. And the apparent wavelength is going to be equal to this. But when we talk about the velocity of the wave relative to the observer, the velocity of the wave relative to the observer is what we gave as v, which is the normal velocity, or the normal speed of the waves in air. So from f naught equals to v over lambda naught, I substitute for lambda naught with this expression here, and I simplified and got f naught to be equal to v over v minus vs times fs. So this was two words. This animation shows what happens when the waves move towards the observer. The separation between the waves becomes smaller when the waves move towards the observer. So the observed wavelength is going to be smaller by an amount which is given by the distance moved through by the source, or by the wavefronts, towards the observer. And that distance moved by the wavefront towards an observer is equal to the speed of the source divided by the frequency. So on the other hand, we are going to see what happens if the source moves away from the observer. So we notice that V minus Vs is less than V. What does that imply? The numerator is going to be smaller than the denominator, and if the numerator is smaller than the denominator, it means this fraction here is going to give us a larger value, greater than f naught. I mean greater than fs. So the observed frequency when the source moves towards the observer, or the observer moves towards the source, is a frequency higher than the normal frequency. On the other hand, we expect the opposite to happen when the source moves away from the observer. Hence, the observed frequencies increase whenever the source is moving toward or towards the observer. But on the other hand, let's try to investigate what happens when the source is moving away from the observer. So in this animation here, we have our observer somewhere here, and we notice that the source is moving in this direction here. We notice what happens to the distance between the crests. We notice what happens to the distance between the crests. So the opposite is actually what is happening, that the source, when the source moves away from the observer, the observed wavelength lambda naught is going to be greater than the wavelength of the source. So in this case, the observed wavelength is going to be greater than the wavelength of the source, but it is still going to be greater than the wavelength of the source by the distance moved by the wavefront. And that distance moved by the wavefront, remember, the distance moved by the wavefront is the extra distance is still given by the speed of the wave, or the speed of the source divided by the frequency of the waves. So in this case, therefore, the observed wavelength lambda naught is going to be lambda, which is the normal wavelength if the source and the observer were stationary, plus the extra distance moved by the wavefront if the source is moving away from the observer. So when I substitute for lambda, remember lambda is V over Vs, and I find the LCM is Fs. This gives us the apparent wavelength as V plus Vs over Fs. Therefore, the apparent frequency is going to be V over lambda naught, which when we simplify, the apparent frequency is going to be equal to V over V plus Vs times Fs. Of course, you must be noticing, therefore, that the denominator this time is bigger than the numerator. In other words, V plus Vs is greater than V. And if the denominator is bigger, it means it's going to make this fraction to cause F naught to be smaller than Fs. Hence, when the source, or even when the observer moves away from the source, when the source moves away from the observer, or the observer moves away from the source, the observed frequency is decreased. The observed frequency is decreased whenever the source moves away from the observer. So therefore, we arrive at what we call the general Doppler effect formula. So this takes us to the general Doppler effect formula. Having seen that the frequency is increased when the source moves towards, so increase is associated with moving towards the observer, and the frequency is decreased when the source moves away from the observer, we come up with what we call the general Doppler effect equation. That is F naught, or the observed frequency, is equal to V over V plus or minus Vs times Fs. I think this equation is given in the list of formula. The last time I checked, this equation was quoted in the list of formula. Our task will be, when do we use plus and when do we use minus? So the convention for plus or minus is very simple. We use a plus sign in the denominator when the source moves away, because away is associated with a frequency which is lower than the normal frequency of the source. And we use a minus sign when the source is moving towards the observer, because towards the observer is associated with an increase in frequency. So every time we use a plus, it's because the source is moving away. Every time we use a minus in the denominator, it's because the source is moving towards the observer. So in simple terms, the word towards or approaches is going to always be associated with an increase in observed frequency. So that is going to be always a minus. And the words away from or recedes are going to be associated with a decrease in observed frequency. And this is always going to be associated with a plus in the denominator. A few things we need to point out when we talk about Doppler effect. Number one, although Doppler effect is most typically experienced with sound waves, it is a phenomenon that is common to all waves, including light or including electromagnetic waves. I have mentioned that. All waves show Doppler effect. In astronomy, for example, the wavelength tends to be measured rather than frequency. That is, in astrophysics and cosmology, we shall talk about this concept. If the measured wavelength of an observed spectral line is less than that measured for a stationary source, then the distance between the source and the detector is decreasing. That is what we would call a blue shift in astronomy, in astrophysics and cosmology. And if the measured wavelength is greater, of course, a greater wavelength means a smaller frequency. If the measured wavelength is greater than the value of a stationary source, then the source is moving away from the detector. So a greater wavelength means a smaller frequency, which would indicate that the source is moving away, which is similar to Doppler effect of sound. When the source is moving away from the observer, the frequency of sound goes down. Similarly, if a source of light is moving away from the Earth, for example, the wavelength observed is higher, so the frequency is actually lower. So it is still Doppler effect. Only that we shall specifically call it a redshift or Doppler redshift. So the blue and red shifts are referred to in this way, as red has the longest wavelength, as we shall mention in astrophysics and cosmology in the visible spectrum, and blue is considered to be the shortest. By the blue is not the shortest in the visible spectrum, but red and blue are the most significant colors of the visible spectrum. So astronomers use the effect to determine the speeds of stars, galaxies, and other celestial objects relative to the Earth, as we shall still see in a unit called Astrophysics and Cosmology, that is for paper 4. By the way, you might have seen the radar systems used by police officers to detect how fast you were speeding or how fast you were driving. So the microwave Doppler effect is used in police radar systems to measure the speed of motor vehicles, and also used for tracking satellites and planes. So tracking satellites and planes is normally done using the radar system, which is using actual concepts of the Doppler effect. Those are some of the applications. Police radar systems to detect how fast you are driving, tracking satellites, tracking planes in space, they are using Doppler effect. So Doppler effect, the concept of Doppler effect is very, very important. Let's first do a few calculations. A train approaching. So the word is approaching. Approaching means the observed frequency is greater than the frequency of the source. A railway crossing at 20 meters per second. So the speed v of the source is 20 meters per second. Sounds a whistle of frequency. So this is going to be the frequency of the source, 440 hertz when 1 kilometer from the crossing. So this is distance. If there is no wind and the speed in air is 320, so this is v, speed of waves in air, what frequency is heard by a stationary observer at the crossing? So remember, is moving towards, is approaching. So the observed frequency f0 is equal to v, and we said if it is approaching, then we use a minus. So it is v minus vs, then times the frequency of the source. Remember the general equation f0 equals to v over v plus or minus vs times frequency of the source. So we just make a simple substitution in this case. So F naught is going to be 320 divided by 320 minus 20. Then we multiply this by the normal frequency of the source, which is 440. Because it is approaching, we expect the observed frequency to be greater than 440. I'll check this with my calculator. 320 times 440 divided by 300. So this gives us 469, which is approximately 470 hertz. So that is going to be the answer to that question. So I've noticed that the observed frequency is therefore going to be 469.3, which is approximately 470 hertz. A car traveling at 20 meters per second has a siren that produces a sound of frequency 500 hertz. Determine the difference between the frequency of sound heard by an observer at the roadside as the car approaches and as it recedes from the observer. So these are two things to consider in the same question: as it approaches and as it recedes. Remember the general Doppler effect equation. And by the way, this equation is always given in the list of formula. F naught equals to V divided by V plus or minus V S times the frequency of the source. So let me say F1 is going to be the observed frequency towards. So the F1 is going to be equal to, because it is towards, the frequency is going to be higher, so I'll use a minus. So this is going to be 330. The speed is 330. So it will be 330 divided by 330. The speed of the source is 20, so this will be minus 20 times 500. That is towards. Then away, I'm going to call it F2. Away is associated with a plus, so this is going to be 330 divided by 330 plus 20. Then I multiply this by 500. So when I press my calculators, 330 times 500 divided by 310. So this is approximately 532 hertz. And the second one is 471 hertz. So we want to find the difference. So I just subtracted the two. So the difference in the observed frequency is going to be equal to 532 minus 471, which is equal to 532 minus 471. This is equal to 59 hertz. Okay. So in my solution, I think I solved this. So in my solution, I quoted the values. Of course, you don't need to quote the values in an exam because there is no such space. I got the frequency towards, I got more significant figures. We expect that the frequency towards must always be higher than the observed, the actual frequency of the source, which is 500. Then I also obtained the frequency away, which is supposed to be less than 500. Then I obtained the difference by subtracting, and I got 60.9. Because here I used the more significant figures, this is slightly different, but it's almost the same as 59 hertz. Okay. A train moving with uniform velocity u sounds a horn as it passes a stationary observer. If the frequency of the sound detected by the observer after the train passes is 1.2 times lower than the frequency detected when it was approaching. Find the speed of the train. So the frequency when it was approaching, let's say the frequency when it was approaching, I will call it F1 is equal to F. That's when it was approaching. Then it means when it was moving, it is lower. So because it is lower, instead of multiplying by 1.2, we shall say 1 over 1.2 times F. So it means F2 is going to be 1 divided by 1.2 times F. So it means we can remember also equate this. When it is approaching, it is higher. And the equation is supposed to be V divided by V minus the speed, which is U, times the frequency, which was F. Sorry, let this be Fs. The frequency of the source is Fs. Then when it was receding, this is going to be V divided by V plus U times the frequency of the source, which is Fs. So I now have two equations which I can manipulate. I have V as 330. So the only unknown remaining there is going to be U, because the others are going to disappear. So when I divide let's say I divide the first equation by the second equation. So I have F divided by 1 over 1.2F is going to be equal to V over V minus U times Fs. Then when I say divide by, I'll get the reciprocal, which is going to be V plus U divided by V times Fs. So VFS cancels out and F also cancels out. So I remain with 1.2 goes up, so I have 1.2 equals to V plus U divided by V minus U. So I just solve this because I'm trying to determine, I'm trying to find the speed U. So I'm just going to just substitute this. So I have 1.2 into V, which is 330, minus U is equal to 330 plus U. So you can open your brackets and collect like terms. So I have 1.2 times 330 minus 330 equals to U plus 1.2U. So I'm just pressing my calculator to find U, because here I have 2.2U. The other side I have 1.2 times 330, then minus 330 divided by 2.2, which gives me 30. So U is going to be equal to 30 meters per second. That was just algebra. So when the train is moving towards the observed speed is going to be equal to that, is a minus. And when it is moving away from the observer, we notice that is going to be a plus in the denominator. And when F2 is 1.2 times lower than F1, we came up with this equation here. So F2 is 1 over 1.2 times F1. And we just divided the two equations. When we divide the two equations, we come up with a simpler expression, such as whether it is V plus U. So it depends on your algebra, whether it is V plus U over V minus U equals to 1.2, or it is the other way around. This is going to give you the same answer. And when you simplify, you still get 30 meters per second as the speed of the train. So here is our questions. Here are questions for us to try out, to just give ourselves a lot of confidence. I'll just give a hint where possible. Michel's alarm clock awakens him with a steady and irritating sound of frequency 600 Hz. Someone told me there is a him in this country who is called Michelle. I didn't know about that. I thought it was a female. One morning, it malfunctions and cannot be turned off. In frustration, Michelle drops the alarm clock, out of his 3-story dorm windows, 15 meters from the ground. Assume that the speed of sound is 340 meters per second. As Michelle listens to the falling clock, so it is moving out from Michelle, that means we shall consider the observed frequency to be V over V plus the speed of the source, then times the frequency of the source. What frequency does he hear just before he hears the clock hitting the ground? So we shall need to find the speed with which it hits the ground, assume that there is no air resistance and therefore the speed is going to be constant. Let us assume that the speed is constant. If the acceleration is constant and we are finding the speed just before it hits, if the acceleration is constant and we find the speed just before it hits the ground, then I will use v squared equals to u squared plus 2as. So v is going to be equal to the square root of, it started from rest, so it is 2 times 9.81 times 15. If it started from rest, then initial velocity is 0. So I'll press my calculator here, 2 times 9.81 then times 15 under square root. So the speed here is going to be around 17, maybe 17.2 meters per second. So that is the speed V of the source, not so this is going to be the speed of the source. So I just substitute in this equation. F naught is going to be this the speed of sound, which is 343 over 343 plus 17.2, then times the frequency of the source, which is 600, which I think should be giving us 570 hertz. You can also verify. The siren of a police car at rest emits a predominant frequency of 1600 hertz. What frequency will you hear if you are at rest and the police car moves at 25 meters per second towards you? So towards you, it is going to be F naught equals to VFS over V minus US. You should substitute and see if you get this. If it's moving away from you, observe the frequency is going to be V times Fs over V plus the speed of the source. You can try to verify if you get that. Remember, the speed of sound in A is given as 343. So you can try to practice that and see if you can arrive at that answer. A car sounds its horn as it travels at speed 15 meters per second. So this is the speed of the source, Vs or Us. Along a straight road between two stationary observers, Mike and Nick. Mike hears a frequency of 538 Hz, while Nick hears a lower frequency. So what does that mean? Most likely is moving away from Nick towards Mike. A car sounds its horn as it travels at a speed of that along a straight road between two stationary observers. So let's say we have Mike here and we have Nick here. And they said Mike hears a frequency of 538, while Nick hears a lower frequency. So the direction of motion is in this direction, is moving towards Mike and away from Nick. Capture the frequency heard by Nick, assume that the speed of sound in air is 340 Hz. So this is very simple. Let's first of all find, we know that the observed frequency for Mike is going to be equal to V divided by V. Because it's towards, it's going to be minus Vs times the frequency of the source. So this means 38 is going to be equal to the speed, which is 340 divided by 340 minus 15, then times the frequency of the source, which is not known. I'm calling it Fs. So I can find Fs here, the frequency of the source. I'll just press my calculator because I'm dealing with A-level students. So I'll just say 538 times, open bracket, 340 minus 15. Then I divide this by 340. So the speed of the source is the frequency of the source is 514, maybe 0.3 hertz. Now the frequency observed by Nick, I'll call it Fn, is going to be V times frequency of the source divided by V plus, because Nick here has a lower frequency, so it is going to be plus the speed of the source, which is going to be 340 divided by 340 plus the speed of the source, which is 15, then times 514.3. So 340 times 514.3 divided by 340 plus 15. So this is giving me 493 hertz, which is approximately 490 hertz to two significant figures. The sound emitted from the siren of an ambulance has a frequency of 1500 hertz. So this is the frequency of the source. The speed of sound is 340, so this is V. Capture the difference in frequency had by a stationary observer as the ambulance travels towards and then away from the observer at a speed of 30 meters per second. I think I've done an example like this one. Let me just check and see which one is the answer, and I just write it here. Okay, let me just solve it. Then the difference in observed frequency is going to be towards is going to be the highest. So towards is going to be 340 times the normal frequency, which is 1500, divided by V, which is 340. Because it is towards, it is going to be minus, so that is minus 30. Then I subtract, because we want a difference. Then away is going to be 340 times 1500 divided by 340. So away is going to be plus 30. So that is going to be the difference. I'll just press my calculator. 340 times 1500 divided by 310 minus 340 times 1500 divided by 340 plus 30. So this is giving me 266. So 267 hertz. You can also verify that a police car travels towards a stationary observer, so it is towards, at a speed of 15 meters per second. The siren on the car emits sound of frequency 250, so this is frequency of the source. This is the speed of the source. Capture the observed frequency. So I'll just write the formula. The observed frequency is going to be the speed of the sound of the waves in air divided by the speed of sound. Because it is towards, this is going to be minus the speed of the source, then times the frequency of the source. So you can substitute and see if you get that answer. I think that should be the end of lesson 5. See you in lesson 6, which will be electromagnetic waves. Until next time, bye bye.